Hey everybody, today we're going to talk about modeling competition. Specifically, we're going to consider a model. Y equals f of x given parameters beta plus lambda and a certain amount of error. Where y is going to be equal to the growth of a tree between two censuses. We're going to have x1 be the DBH of the tree. But we're also going to have x2 being equal to competitor biomass. Let's take a look at a picture. Let's take a focal tree of interest in red. Surrounding that tree are competitor trees of different sizes. As trees get larger, they take up more, they have a lot more biomass. So the question is, as you have more competitor trees in black surrounding that focal tree, how does that impact the growth of the red tree? But not only does the number of tree matters, but the size of the tree matters. So we're interested in competitor biomass's impact on the growth of that red tree. Here's the model we're going to use. Y, the growth, is going to be based on 1 beta, based on the intercept, beta dBH, the slope for dBH times dBH, the idea being that you want to account for that tree's size to begin with, because, for example, a younger tree will be smaller and therefore will grow more than an older tree. So basically, you want to account for the starting dBH. But here's where it gets interesting. Plus lambda times competitor biomass. Meaning, you add up all the biomass of all the competitors, compute BM, and then you have the slope for that BM. And sorry, this should not be in a different color. Let's go back to blue, plus an error term. So the F here, this F over here, is simply multiple regression. Okay, so then you fit your regression as you normally would, and you get fitted values, y hat, which are based on a fitted intercept and fitted slopes. And by plugging in values into this equation, you can get fitted values or predicted values y hat. All right. So that is one model. This is right here. One model for competition. Great. But now, let's go back to this case here. Notice how in this image, we make no distinctions between the different competitor types. What if a more accurate model for competition is this one? The location and size of the dots are exactly the same, but now we are making distinctions between species. So now we are taking into account the species of the competitors. Let's go back. So going back here, this model for competition, one model for competition that does not distinguish between competitor species. Let's now write out a model like this one up here that does distinguish between competitor species. It's going to be similar. Y equals beta naught plus beta dBH times the dBH of that tree. But here is the change. Plus lambda oak times the biomass of oaks. We now make distinctions. Lambda, the slope for maple times the biomass for the maples, plus lambda birch times the biomass of the birches. You can see we are now making distinctions between the different species. So this is a model that does distinguish between competitor species. Let's call this model 2, and let's call this one model 1. All right, let's now do a parameter count. A parameter count. Model 1. How many parameters are in model 1? 1, 2, 3. We have 3 parameters: the intercept, the slope for dBH, and the slope for biomass of all species put together. 3. Next, model 2. How many parameters do we have? 1, 2, 3, 4, 5. Because model 2 has 5 parameters and has many more terms, this is a more complex model. Meaning it's just more meaning it's more complex. Meaning there are more parameters to estimate. Parameters to estimate for the same sample size. Because you have more parameters to estimate with the same sample trees, your estimates are not going to be good. So here is the question. Is the additional complexity of model 2 over model 1 warranted? Is the additional complexity of the model that distinguishes between the species versus doesn't distinguish the species worth it? And that basic principle is Occam's razor. Occam's razor states that all things being equal, simpler is better. Meaning, I'm only going to choose model 2 if that complexity is warranted. That's all I can fit for now. We're going to revisit this later.